I've talked about separation of variables. Well, I've used the phrase. Let's actually look at it in a bit more detail of what separation of variables is. A first order differential equation, that's what we're dealing with. It is what we call separable if you can write it like this. If the derivative can be simply written as some function of x times some function of y, then you can separate it out and do your integration. Now notice when you go from the derivative step to the next step, that's when you throw your integral signs in. You don't normally write the line just the y over gy equals function x dx. You normally whack the integral signs in straight away when you do it. Now the thing with this is we lose trivial solutions because of course you can't divide by 0. There often will be a trivial solution that gy equals 0. That may well solve the problem. So you just need to do a bit of a check. You just look at it and go, oh yeah, that works or that doesn't work. Something like this. dy dx equals x squared 1 plus y squared. In this case, there won't be trivial solutions because I'm going to divide by 1 plus y squared, and 1 plus y squared can't equal 0. So I won't get any trivial solutions with this. So we'll separate the variables out. On the left-hand side, we've ended up with inverse trig. On the right-hand side, it's just a polynomial. So let's integrate. Inverse tan of y is x cubed on 3 plus, it really doesn't matter where you put the constant, on the left-hand side, on the right-hand side. There's just a constant in there somewhere. If I want to make y the subject, which is probably why it makes more sense to put the constant with the x, we'll get the tan of x cubed on 3 plus a constant. dy dx equals x squared y. Now in this case, we do get a trivial solution because it's a possibility. Y could equal 0, that certainly could happen. And if you were to substitute it in, what would happen? Well, dy dx would equal 0. Integrate 0, you get a constant, and well, 0 is a constant number, so yes, it is a solution to this problem. Separate the variables to find the other more interesting solutions. So dy on y is x squared. We get the log of the absolute value of y is x cubed on 3 plus a constant. Now that means the absolute value of y is e to the power. And of course I can use some index laws here and I get e to the power of c. Well, e to the power of c also is just a constant. In this case, because I'm saying absolute value equals, that constant must be a positive number. But then when I make y the subject, it's no longer necessarily positive because I would say, well, y equals plus or minus. So I just changed it to a rather than c. Do I really need to do that? Maybe not. But it's sort of highlighting that, c is positive, but a doesn't necessarily have to be positive. But of course, that's not my final answer because there is the trivial solution as well. So there's two possibilities. Y could equal 0 or y could equal some constant times e to the power of x cubed on 3. Okay, let's do a particular solution. So dy dx is cos y on x squared. By the way, I'm going to use definite integrals for this. Makes more sense rather than finding a constant. Well, here's how I separate it. Because of course, cos squared, when I turn that upside down, I just simply get sec squared. So actually, yeah, I can separate these. So we get sec squared y to y, and on the other side, dx on x squared. Integrate sec squared, we get tan, and of course 1 on x squared, that's one of our common ones, minus 1 on x. Substituting in, playing around with it, make y the subject, and there it is, inverse tan of 2 minus 1 on x. How on earth am I going to separate this one? X squared plus y squared over 2x squared. So it certainly looks like something that's not separable, but it is via a use of clever substitution. You see, if I think of this as a function of y on x, then I could rewrite this fraction to be a half plus a half y on x squared. So if I let u equal y on x, in other words, y is u times x, that's what I'm going to do. But then I have to substitute in completely. I'm going to eliminate this y on x, so I don't really want the y dx. Let's find out what that is. The y dx is, well, u times x, I've got to use a product rule. Write down the first, u, diff the second, or differentiate x, I get 1, plus write down the second, x, differentiate the first, I get du dx. So now I can do a complete substitution and get rid of the pronumeral y. Now I've got something that can be separated. So I end up eventually with x du dx is 1 minus u squared on 2. Let's now separate our variables. 2 times the integral of du on 1 minus u squared is the integral of dx on x. So 2 on 1 minus u is the log of x plus some constant. I've made u the subject, but of course that wasn't the question. I've got to get y back in there now. So u is y on x, sub that in. Now I just got to multiply by x. I have my answer. X minus 2x over the absolute value of log x plus a constant. Would you have spotted that? Who knows? But you've got to think of some of these ideas sometimes. Might not look separable when you first look at it. Clever substitution, you end up with something that can be separated. So 13C, we're going to separate our variables.